So I'm no longer a postdoc at the UCSD, but I was when we did a lot of this work. So we put on anyway. So I'm happy that Mario spoke first, because it basically turns out that he has said most of what I was going to say. It turns out that our work overlapped a lot. I was actually not aware that it was that close, but very interesting to see. Now, I will skip the introduction a little bit fast. We're also a little bit behind, I think. So essentially, like Mario said, QSAR is built on the assumption that molecules have like similar function if they have a similar structure. And it's a relatively old field where people have come up with all kinds of, features and put them into different types of models. QSAR has kind of come a long way. In addition to descriptors, there's also now a bunch of, molecular dynamics, quantum mechanical simulations, all this kind of stuff. But this is, I'm under the impression that this is kind of the seminal paper in this field. So a lot of the inspiration from this work is actually from this relatively new cell paper, where they discovered a new antibiotic by a strategy that kind of looks like Mario's, but instead of using like meaningful descriptors, they have a neural network learn some descriptors that it thinks describes the molecules better. So the big difference between what I'm doing and what Mario is doing is that we are not using descriptors that are meaningful in that sense. We are trying to do this from molecular networking. And so essentially, a lot of you probably know what molecular networking is, so I don't have to go into a lot of details here. But essentially what you get out from molecular networking is like MS2 spectra that will often have some kind of characteristic peak for certain functional groups. And obviously you can take all this data and you can try to learn directly from it. So we essentially try to replace the molecular descriptors with just the fragmentation data. The advantage of this strategy is that we have a lot of untargeted metabolomics data in the world. We have a lot of data generated in this fashion that it would be nice to learn something directly from, because often we cannot assign a structure to an MS2 spectra that we have acquired. So if we could learn directly from this, it would also mean that we could apply our model directly to untargeted metabolomics data and make predictions about bioactivity. At least that's kind of the goal here. Now, where do we get it from? We get it from GNPS. A lot of you probably also know GNPS, so maybe there's no reason to spend a lot of time going into this. But obviously they have both a huge library and huge data sets that you can actually use to do interesting things with. The first thing that we kind of need is to build some features to present to machine learning algorithms. Like, they will not, spectra suffer a little bit from the problem that they are not a discrete thing. So the way that we discretize them is basically by binning them. We just put like a little window around on across the entire MC range and say, okay, we will put everything that's from this to this into the same feature. And so to do this, a lot of people have kind of built this software a little bit half-sidedly because they need it for their own application, but we wanted to build something that was like robust and something that was memory efficient, because we are trying to apply this to very large data sets. So we want to use these kind of sparse matrix representations that you can use to present your data to, for instance, a lot of the algorithms in scikit-learn, like they also call this stuff. So it's a very nice, efficient way of representing it. There is also immediately a lot of questions about How big a binning window should you use? Should you do some kind of filtering for some peaks that you're not interested in? All these kind of things that are a little bit outside the machine learning itself, but is still a hyperparameter in a sense. And we support a lot of those objects. So we have also done a bunch of benchmarking to figure out what are sensible defaults for these options. And it's all kind of implemented here. We tried to make some visualization. I will not say that that's our best feature right now. Arjun has made it like a big package, so it's relatively easy to install. Now, just like Mario, we also need some training data, but unlike Mario, there isn't a lot of databases out there that will directly give us MS2 spectra annotated to activity. So basically, we have to build some software that will take all the pumpkin data that Mario just talked about, that has been annotated with bioassays, or whenever people do an assay, they kind of upload the result here. To get the spectra, we are going to the GNPS library. So essentially, what this software does is that it merges like things that we have spectra for and things that we have bioactivity for. And that's kind of the key to building our training sets, because we need both of those types of information. And obviously, as you know, there's a lot of stuff in Pumpkin. So what are some of the problems here? Like when you don't have the structures, but only the fragmentation spectra, there's also some technical problems, I would say. Challenges, I think it's fair to call them. Number one is just that they are acquired in very different ways. And one of the things that we actually know that are different is what machine were they acquired on. So in the GNPS libraries, which is where we get the spectra, there are, I don't know, maybe 30 different machines represented or something like that. This is only the subset of them that are QTOS, because otherwise the table is huge. I have tried to represent it here in the way that we built the training set, because we try to build balanced training sets between the bioactivity that we're interested in. Here it's antimicrobial bioactivity that we can identify in the PubChem database. And so when I try to look at these balanced data sets we did with random molecules and bioactive molecules, and try to see, is it actually balanced between the machine types? The answer is sometimes. But it's not something we can guarantee, and it's very hard to build in constraints that will give us, at least it's not obvious how to build the constraints that will give us balancing across technical factors, because there are also other things, including things that we don't know about, like chromatography and the electron volt settings on the fragmentation. Now, another technical problem here that I've also tried to represent in this table is that because we get the spectra from the GNPS libraries, we need to know that they are somewhat representative, because some of the GNPS libraries only contain things that are drugs, for instance. And that's actually not quite what we're most interested in. We are most interested in natural products. But the drugs are also where a lot of the antibiotics are. So we kind of have to work with what we have in some sense. But there is some bias here in the way that we select spectra from the library, which is a little bit hard to get around, I would say. So just to, this is kind of a case study, I would say. I've tried to take all the molecules and represent them as a UMAP representation over here, where 0 is no activity and 1 is antibiotic activity. And it's not totally clear that those are separable in that space, at least. So what we have done is go through a whole bunch of hyperparameters, both for all the mass spec related stuff like binning size and filtering options, but also just machine learning algorithms, what actually works here. And what we have ended up with is that XGBoost seems to be the solution that works. We have actually also tried a bunch of neural networks, which I emailed Mario about like a year ago, so I think we just found out. But yeah, what we have settled on is this XGBoost, and it actually works fairly well. Like AUC of 0.73 is not the worst you could come up with. Oh, this is, now that I think about it, this is the random forest. No, but I think I mixed some figures here. It's not so good. This is the XGBoost numbers, and they are substantially better. So what we try to do with the XGBoost algorithm, you can also get some feature affordances. And this is important for us because ultimately we believe that the specific functional groups are the ones that kind of convey the information about the activity. So it's kind of important for us to try if we can annotate exactly what are the features that does something for prediction here. It also turns out that like some of the filtering we do is try to get away to remove the parent masses first. But it looks like some of them still remain in the MS2 spectra. So I think we need some better filtering options here because they are very predictive and it's not so useful for generalizing. So I have tried to take what we have developed, like the final model that we thought was best, and then apply it to this actinomyces data set here that you can find in GMPS. They have a whole bunch of structures over there, and there's a lot of them that I would predict have antibiotic activity. But actually, when we apply the model, we only get one feature with very high probability. So I think like even though we do relatively well on training set test set splits, it seems like we cannot yet generalize super well to natural products. And yeah, so just to summarize a little bit, we have developed some software for the upstream steps of this. We have built the framework for like generating training sets that are useful, and we have like done a bunch of work to try to figure out how do we actually even get some working models out of this. And on the test set, we have, like, if we hold out a test set from the actual training set we built, it's pretty good. But I think there is a bunch of work to be done in the sense of picking the negative set. Because that also has to be somewhat representative of all the molecules in the world, and it's a little bit hard if you only have a couple of thousand. I think one of the major things that I took out of Mario's talk, and that we should talk about afterwards, is that there are a bunch of these functional groups that are highly predictive, but they are not useful in a natural product setting, or they don't generalize well in that setting. And so obviously there is, for instance, things like fluors, which there is a lot of in synthetic antimicrobials, but they are not very useful in natural products to predict stuff from. Mario has also other molecules, and I think that was pretty clever that we should talk a little bit about how to filter those out. We need some kind of systematic way of doing this feature annotation type of thing with functional groups, because it's too manual right now and it's not useful in this sense. But I think if we can combine all these things with things like the serious chemical prediction, like they have some new class prediction tools and stuff, I think it will be pretty helpful to actually get closer to something that looks like real bioactive molecules. So, work in progress. I guess. Thank you.